Hello, in this video we are going to be working through our next worksheet, which is on section 2.8. Now in section 2.8 we have two topics in this section. First off, we're going to talk about linearizations, and then also we will talk about what are called differentials. So in this video we're going to focus on linearizations. Now let's think back to what the equation of a tangent line is. If you recall, we get the slope by finding the derivative of the function and evaluating it at a point. We can get a y value on our tangent line by evaluating our function, not the derivative, but the function at the point. And then, of course, our x value is just whatever that point is. So plugging into our point slope formula, then we have y minus f of a is equal to m, which is f prime of a times x minus a. And now if we solve for y, we get f of a plus f prime of a times x minus a. And this function here is called the linearization, or a linear approximation of f at a. And since we call it a linearization, we normally denote it with an L of x. So L of x is equal to f of a plus f prime of a times x minus a, and that's what we have in our figure here on the right. We have our tangent line, which is labeled as y equals L of x, that's our blue line. We have our curve in black, that's labeled as y equals f of x, and notice we are finding the tangent line at the point a, f of a. Now if you'll notice from this figure on the right that if we consider x values pretty close to a, so let's say in between here and here, where x equals a is right there, if we consider values there, then our blue line and our black curve are almost indistinguishable, meaning that the function values are very close together, very close to each other. So what we have then is that the linearization values are approximately equal to the function values for x values near a. So we can use this property of the linearization, that's why we sometimes call this a linear approximation. We can use this property that the linearization approximates f to get approximate values for the function if the function is a hard function to evaluate. So for example, let's say we consider f of x equaling x to the 3/5. For particular x values, we might be able to evaluate this exactly, but for a lot of x values, we can't. Whereas if we have a linear function that is close to f of x equaling x to the 3/2, linear functions are very easy to evaluate. So we are going to find the linearization of f of x at x equals 32. Now at x equals 32, we need to find what that value is. And notice that when x is 32, we can write the 3/5 power as 32 to the 1/5, all cubed. Now 32 to the 1/5, the fifth root of 32, that's going to be 2, because you can raise 2 to the 5th power in order to get to 32. So now we have 2 cubed, and that is 8. So x equals 32 is one of the few values that we can substitute into x to the 3/5 and get fairly easily get an exact value. So we have what our y value is. This is our y1 value. We also have our x1 value, and we need our slope, so we're going to have to find the derivative of f. We will use the power rule here, bring down the power 3/5 and subtract 1 from the power. We're going to get a negative 2/5. So then that will give us f prime of 32 being 3/5, 32 to the negative 2/5. Now similarly to what we did when we substituted 32 into the original function, we can take 32 and raise it to the 1/5 power. And then we would take that whole thing and raise it to the negative 2 power. So 32 to the 1/5 is 2, as we already saw. 2 to the negative 2 power is going to be a 1/4. So we have 3/5 times 1/4 or 3/20. Now all of this together will give us what our linearization is. So the linearization, according to our formula, would be f of 32 plus f prime of 32 times x minus 32. And plugging in the values that we have, f of 32 is 8, f prime of 32 is 3/20, and x minus 32, and we could rearrange this if we wanted to, but we don't have to, and sometimes it's actually easier to evaluate x values near 32 if we keep it in this form. So this would be our final answer for number 1. L of x is equal to 8 plus 3/20 times the quantity x minus 32. So that's finding linearization. Now, if we look at number 2, we are going to use this linearization to approximate the 5th root of 32.1 all cubed. Now we need to relate this back to the function that we had in number 1 so that we can use the linearization that we found in number 1. So notice that 32 to the 5th root of 32.1 cubed is the same thing as 32.1 to the 1/5, all cubed, which is the same thing as 32.1 to the 3/5. So if we were substituting this into our function, f of x equals x to the 3/2, this means that x is going to be 32.1. Let me rewrite that. 32.1. And this is since f of x is equal to x to the 3/5. So then the 5th root of 32.1 all cubed, which is equal to f of 32.1, that should be equal to the linearization evaluated at 32.1. So we're going to take 32.1 and we're going to plug it in for x in our linearization. So that's 8 plus 3/20 times 32.1 minus 32. So notice 32.1 minus 32 is easy to evaluate. That will give us a 0.1. So we have 8 plus 3/20 times 0.1. And if we find our decimal approximation, we get exactly 8.015. But the problem says to do it to 4 decimal places, so we'll just go ahead and add a 0 there since it's 4 decimal places. So what we ended up getting then was the 5th root of 32.1 cubed is approximately equal to 8.015. And that wraps up our solution for number 2.